So I always get asked, what am I going to use this for in the real world? Well, your test, which we'll be taking shortly. But more importantly, like, this is how everything that we have and own, computers, cell phones, smartphones, satellite dishes, all this stuff works on math. And the way that we figure this stuff out is through observation. All of physics is from observation. And so we collect data and we compare, does this parameter have an impact on that parameter? Let me give you an example. The time of the year, position of the Earth, does that affect the temperature? Does the amount of water or the amount of rain, does that affect crops? So you have all these factors or parameters that have some sort of mathematical correlation. And we can write equations, and those equations can help us to make predictions. And if we know what those predictions are, nobody here understands how gravity works. We don't know if something falls to the ground like that can just did. We don't know what causes it to fall to the ground, but I can calculate and tell you based on the height of that desk and the acceleration due to gravity, I can tell you how many seconds it'll take for that can to hit the ground. And the reason I know this, Sir Isaac Newton, several hundred years ago, just dropped a bunch of stuff, did some math models, came up with a few equations, and I'll use those same equations and I'll calculate mathematically how much time it will take for that can to hit the ground. So what we're going to talk about today are linear models. So let me give you an example. So if I have a graph and I'm comparing two things, and I measure things, and we've been talking about dependent and independent variables. So I'll give you an example. Let's talk about the age of an individual, and we'll compare that to their height. Now I'm going to purposefully not put in any numbers because the numbers don't really matter. But it would make sense if I took all you kids in here and I measured your height when you were a year old and when you were 2 years old and 3 years old, and I just plotted the points. What you would see is you would see all the different kids and the different points. And you would have all these points that look like this. Scatter plot. Yeah, and it's a scatter plot. And so if you look at that, you would say, hey, that almost looks like a line. Right? So I could write an equation of a line. And that equation of the line can help me predict the behavior of somebody's growth. Actually, let me change it to a different color. So I could write some equation of the line, y equals mx plus b, that fits that data. So when we do linear models, we're looking for a mathematical model to predict behavior. Okay? So you guys don't know this, but there's a mathematical model out there that when they measure your height at your 2-year-old checkup, whatever that height is, if you double it, it's pretty much how tall you'll be as an adult. Okay? How do they know that? They just measured a bunch of kids' heights. Every time you go in for your annual checkup, the doctor's first thing they do, they weigh you in, they measure your height. Some mathematician somewhere sat down and said, I noticed that when they're 2 years old, they're exactly 1/2 the height they are as an adult. It's not exact, but it's pretty darn close. It's a pretty good indicator, right? And so that's based on a linear model. So what I'm going to do is I'm going to draw. For example, number one, I could take a picture and put it on the board, but basically, for example, number one. And this is in your textbook on page 93. So if you want to look at a little bit better version of this, you can. But basically, they have a table of values, okay? And they have the month, and they have the temperature, and then they have the electricity bill, all right? So this would be like January, and so this would be the month. This would be the temp. And this would be the electricity bill. Okay, so the average temperature was 61 degrees Fahrenheit, and the electricity bill was $150. In February, the average temperature was 58 degrees, a little colder than. The electricity bill was $139. In March, the average temperature was 67 degrees, and now the electricity bill was a little higher. Now, why might the electricity bill go up a little bit as it gets warmer?
AC.
Maybe they turned on the AC. So now as we crank over to April, and by the way, this is a very warm place. 75 degrees in April, that's not too bad, but now the bill is $205. And we'll do June, or no, let's do May. 79 degrees, and the bill is $170. Okay, so there's a little bit of an anomaly. We'll keep going. For June, we've got 83, and the electric bill was $234. And so, if I were to graph this, see, as you look, it looks like as the temperature increases, so does the electric bill. So sometimes, like Mr. Adams has his electric bill on a monthly payment thing, what they do is they average out and figure out what my bill would be from month to month, and I just pay that. I like it that way. It's kind of a budgeted thing. I think for my big house, I think it's like $100-something. It's a little more than $100. But the actual bill in the month of July, because I have a 5-bedroom house with air conditioning.
But dude, why you have
it's
showing off.
Well, it is.
Have one room houses.
My electric bill is pretty high. It's like it's over 200 sometimes. So it's a high electric bill. But now I have gas heat.
4 degrees.
Why is it bragging? I have 4 kids. How else would I do it?
There's 3 kids in my house.
Right, for what it's worth, it's an old crappy house.
I have a 2-bedroom house. We had to build the 3rd one.
Did you?
Yeah. In the basement.
I'm sorry.
I'm sorry.
By the way, that's in the video. I gotta edit it out. So now, if we look at this, January, February, March, April, May, and June, and then I'm gonna count by like 50. So like here's 50, here's 100. These are the electric bills, right? And 200, and then we got 250 over here. So my first point here, if I kind of graph it like that, I've got 61 degrees in January. Oh wait, I got to compare that. Oh, let's do that a little different. This is January. So instead of doing it that way, let's do the temperature, because we see that there might be some sort of correlation between the temperature and the cost. So I'm going to put, I don't know, let's count by tens. Maybe we'll do 50, 60, 70, and 80. All right? And we'll do 90. So there we go. Okay? And so now if I go to plot this, if I go over 61, which would actually be about right here, my bill is 150. So it's about right there. If I go 58 for this next point, 58, 139, I got a point here. If it's 67, which is about right here, my bill is 172, which is about right here. The next point, 75, 205. 75, which is right here, is about 205, which is about right there. 79 degrees is 170, so 79 degrees is about right there, and I got a point about right there. And 83 is 234, so 83 is about right here, so about right here. And as you look at that, you can see that there's a trend. And if you look at the summer months, and I didn't write them all down, that trend continues for the rest. So as the temperatures start to get into 80 and 90 degrees, the bills start to go as high as 255 is the highest bill in July. And so is there a possibility, let me do a different color, is there a possibility that I can figure out some sort of math correlation? So, yes. And so this scatter plot reveals that yes, there's a strong positive correlation between the temperature I ran out of space to write the word correlation. But there's a strong positive correlation between as the temperature increases, so does your electric bill. Does that make sense? Okay. Let's move on to example number 2.